Yes.
Okay.
All right. So our next speaker will be Ethan Lake from MIT. Please go ahead.
Okay, awesome. Yeah, thank you, Dominic, and thanks to the organizers for giving me a chance to speak. I think this conference has been pretty awesome. Yeah, so in light of the time limit here, I'm just going to talk about something which is very simple. I think I can get everything across in 15 minutes, but it's simple but maybe useful for people working on Fractons to know. This is work that I've been doing with Mike, and it's been languishing on our computers for a very long time, but hopefully it'll be on the archive at some point. Yeah, and then also let me say that I just I got my second dose of vaccine yesterday afternoon, and my immune system is like very, very unhappy with that. So please forgive me if I am less lucid than usual. Okay, so the motivating question for this talk is to think about what kinds of continuous quantum phase transitions can occur between a fracton phase and some other different type of phase of matter. Now we've already heard a little bit about phase transitions in fracton models so far in this conference, but the approach I'm going to take today is going to be very simple-minded. We're just going to look at some phase transitions that occur in the Xcube model, which we all know and love. And basically what we're going to do is we're going to condense various excitations in the Xcube model and see what resulting phases we get and what the phase transitions look like. Okay, so let's just jump right in. So Kevin already did a very good job of summarizing what's going on with the Xcube model. So this slide is really just to get people used to the sort of pictures that I'm going to be drawing in the next few slides. So we're going to be interested in the ZN Xcube model. The ZN Xcube model has a Hamiltonian, which pictorially I could draw as the terms in the bottom left. So since we're interested in the ZN Xcube model, we're going to have poly X's and poly X daggers, and we need to keep track of the difference. And so that's why the dots are different colored. Anyway, so of course, as we already heard, the Xcube model has two distinct types of excitations. So one type are called linons. I'm going to write them as EXYZ here, where the superscript denotes the direction along which they can move. They're one-dimensional particles. And they obey this fusion rule EX, EY, EZ is equivalent to the vacuum. And the second type of excitations are fractons, and they're created at corners of membrane operators. Okay, so this should be familiar to everyone. So what we're going to do is we're going to just condense various excitations in this model and see what happens. So first, let's consider what happens when we try to condense linons. Now, before talking about the phase transition that could occur at the condensation phase transition, let me just discuss what we expect the resulting condensed phase to look like. So first, consider just condensing one species of linon. So for example, let's just consider condensing EZ, which can move along the Z direction. What this does is it turns the EX or EY particles into planons. So in the condensed phase, they can now move in 2 dimensions. And the reason for this is very simple. So if you recall, the reason why EX or EY or EZ are linons in the Xcube model is because if I try to lay down a string operator which moves an EX or EY around a corner, it leaves behind an excitation at the corner point. So in this picture that I've drawn, I have an EX at say the yellow star. And if I try to move it in the Y direction, then the place where the string turns a corner nucleates a EZ particle. And this costs energy in the Xcube model. But of course, when we condense EZ, then there's no problem in doing this because we can absorb an EZ from the condensate. And what this means is that in the condensed phase, the EX turns into a planon capable of moving in the XY planes. And so a natural guess for what the resulting condensed phase is simply a stack of a bunch of 2 + 1 dimensional deconfined ZN gauge theories, where the stacks are in the XY plane, and the gauge charges of the ZN gauge theories are identified with the E particles. Okay. And indeed, okay, this guess turns out to be correct. You can do some sort of generalized gauge theory construction where this can be shown, that what exactly goes on in the condensation transition can be shown in detail. I'm not gonna talk about that for time. Okay, and then let's also say, just for completeness, what happens when we condense multiple species of linons, right? Actually, this is pretty trivial. So because of this fusion rule here, if I condense both EX and EY, well, their product, EZ, is also condensed. And so all the line-ons are condensed, and actually this phase is trivial. Okay. So let's now look at the phase transition, or one possible phase transition that can occur when we do this condensation. Well, the natural one natural guess for what a phase transition here could look like is the following. So since we're condensing objects which move along one dimension, it's natural to look for a critical point which is described by a sort of array of 1+1 dimensional Zn clock models at criticality, right? So I've tried to kind of draw this in the picture to the right. And then we can ask, and indeed in this generalized gauge theory construction thing that I'm not going to talk about, you can show that this is sort of the critical point that is realized in that construction. Anyway, so what we would like to do is we'd like to evaluate the stability or lack thereof of a critical point like this. And it turns out that whether or not critical points like this are stable with respect to couplings between the wires and stuff like this depends on the value of n. And so if n is less than or equal to 4, it turns out that there's no obvious stable critical point here. So usually when n is small like this, there are some operators that couple these chains together, which lead to trivial gap phase. So that's not to say that there are no continuous, there are no stable critical points, but I just haven't found them. And if they do exist, they don't look like what I've been describing. On the other hand, when n is large, so this is a familiar fact, right? When n is large in these sorts of scenarios, you can use a U1 description where you treat the Zn variables on each chain as in a U1 description with some anisotropy, and that anisotropy is irrelevant at the critical point, and you can use U1 variables. So what we do in this example is we take the easy line-ons and we write them in a density phase representation with the fields phi and theta. This will be familiar to people who have worked on Ledinger liquids before. And the details are not important, but you get some action that looks like a bunch of Ledinger liquids arranged on this array. And okay, so you can examine what the stability of actions like this. And it turns out if you are judicious about how you choose these derivative couplings between the chains, this G and these H parameters in this action, you can create critical points which are stable and have no relevant deformations. So essentially what this gives us is, in fact, the region of parameter space which this action is stable is, it occupies a sort of finite region of parameter space. And what you get in a scenario like this is a sort of a critical phase or a gapless phase, if you will. You start from the Xcube model and you condense these line-ons, and there's an intermediate range where you have this kind of gapless fixed point. Okay, so that's one example of a way to produce a continuous phase transition in the Xcube model. Let's talk about another example. So the other example comes from condensing objects which can move in 2 dimensions. And so in the Xcube model, there are a few types of such objects, but I'm just going to discuss one of them for concreteness. And that is a bound state of 2 fractons in sort of a dipolar configuration, as is drawn on the screen. So these bound states of fractons come in sort of 3 flavors labeled by the direction along which their quote dipole moment is pointing. So in the picture, these quote dipole moments point in the z direction. And these sorts of objects can be, they're planons, and they can move in planes orthogonal to their quote dipole moment. So in this example, these z dipoles that I've drawn can move in the xy planes. And so we can ask, of course, what happens when I condense these objects, right? And again, what exactly happens depends on sort of how many of these objects you want to condense. So let's just look at let's just condense these z direction dipoles at first. Now, what happens is, okay, so consider condensing these z dipoles, right? Now, in the condensed phase, isolated fractons are still not locally creatable. and so they remain as deconfined excitations. But if I take a isolated fracton and I fuse it with one of these sort of Z dipole guys in the condensate, I can make it hop along the Z direction, right? Just by virtue of the shape of this condensed excitation. And so what this means is that in the condensed phase where these guys are, where the Z dipoles are condensed, single fractons, isolated fractons, become capable of moving along the Z direction. And so they turn into sort of line-ons. And in fact, the model that you produce by performing this condensation is some kind of weird anisotropic model that was actually studied by Wilbur and Kevin and Xie a few years ago. Okay, now let's ask what happens when we condense an additional flavor of this dipole. Well, if we condense, for example, dy, then the same kind of reasoning means that isolated fractons now, by fusing with the condensate, are free to move in both the y direction and the z direction. And so a natural guess, and which is indeed borne out in some sort of explicit generalized gauge theory construction, is that the phase that you get upon doing this condensation is, again, a stack of Zn deconfined 2+1d Zn gauge theories. In this example, if I'm condensing y and z, then these stacks would be in the YZ planes. And the gauge charge of each gauge theory in the stack would be identified with an isolated fracton. Okay, and then finally, we can ask what happens when we condense all types of these sort of dipolar bound states. When we do this, an isolated fracton now, by fusing with the condensate, can move in all 3 dimensions. And one guess about what the resulting phase looks like is a 3+1 dimensional deconfined Zn gauge theory, with where the gauge charge is again an isolated fracton. And again, this is borne out within some sort of explicit construction that we can account. Okay, so then finally, let's just look at the critical points, or one possible set of critical points that occur when you perform this condensation. So let's, for simplicity, let's just ask what happens when we just condense one sort of orientation of these dipoles. So again, let's think about the Z orientation. Then the natural critical point that you would be prompted to write down, and indeed what occurs in some various explicit models, is a critical point that just consists of a stack of 2+1d critical Zn clock models. So it's essentially just the same sort of idea as in the line-on condensation case, except here we're just in the critical theories, the critical fluctuations occur in one higher dimension. And okay, again, like in the previous case that I was discussing, whether or not these types of critical points are stable with respect to deformations depends on n. And again, n equals 4 is this number that comes up a lot in when you're doing thinking about RG and critical phenomena. When n is less than 4, there's no obvious stable critical points that I could find in these models. You usually, when n is small enough, you have energy couplings between these planes, which can drive the system to some sort of gapped state. And so that's less interesting. But however, when n is greater than or equal to 4, then again, what we do is, you use some sort of U1 description, because the
sorry, Ethan, one more minute.
Okay, yeah, great. You use some sort of continuum. You use some sort of U1 description. You write down a stack of XY models, which would have the form given in the equation. And a happy fact is that it turns out the most relevant deformation to this critical point is energy coupling between layers. And a happy fact is that the scaling dimension of the energy operator in this CFT is very slightly bigger than 3/2, which means that the deformations to this fixed point are very, very slightly irrelevant, and you get a stable critical phase, a stable critical point. And okay, that's all. Here's my summary slide. So I'll just end there, and thank everyone for listening.
Okay, thanks.